Welcome to our session on side channel attacks, our favorite topic, judging by us being here. Our first speaker will be Kai-Chun Ning, who will speak about finding and protecting the weakest link on side channel attacks on Y in mask MLDSA.
Hello, everyone. Thank you for coming, and thank you for the introduction. This is a joint work with Julius Hemmerling and Risha Patri, and we are from the Max Planck Institute of Security and Privacy. And as quantum computing becomes better and better, it's expected that the classic asymmetric crypto that we rely on today will be broken in the future at one point. And for encryption, it's obvious we need to migrate. And this is also the case if we have a long-term public key infrastructure. And to address this threat, NIST has standardized the so-called MLDSA, or modular lattice-based digital signature in full, as the new quantum-resistant signature skins. And this signature skin is based on dilithium and uses the Fiat-Shamit with abort peridrine. And what this means is that maybe it's better to illustrate it with simplified algorithm. So here in algorithm one, we could see the simplified signing algorithm. So we have a public matrix A. We have a secret polynomial S1, and we want to produce a signature for a message M. What we do is that we first sample a random polynomial Y, and then we compute A times Y, and then we take the hash value of the message M together with part of A times Y, and this becomes the challenge C. Then we compute Z, which is Y plus C times S1. And then we need to test if this Z leaks any sensitive information. If this is the case, we have to sample a new Y. And we will continue to do this until we sampled a Y such that the resultant signature Z leaks no information. Then we output Z and C as the signature. And this signing algorithm has been analyzed, and there has been many side channel attacks on this signing procedure. And they are listed on the right-hand side of this slide. I will not go into the details. You could find the references later, and they are interesting. What is important is that those side channel attacks were not conducted on a protected or properly protected masked MLDSA implementation. And the last one, which is a Saska framework on CS1, analyzes if we could defeat shuffling with Saska. It turns out to be the case, but they did not analyze if this will work for mask MLDSA. And many of those attacks, they do not tolerate noise that well, so it's unclear if they will apply to a mask MLDSA implementation. So what is masking exactly? It's actually very simple. So the basic idea is you want to split a secret value into multiple shares, and only when you know all of those shares, and by combining them, you obtain the original secret. And there are two common masking types. You have Boolean masking and arithmetic masking. So for Boolean masking, it's very simple. You just XOR all the shares, you obtain the original secret. And for arithmetic masking, you have to define this over modulus Q. Then the sum of all shares mod Q is the original secret. And we further define masking order as number of shares minus 1. And because of the extra memory and computation overhead in practice, you will not use a very high masking order. If you use masking order 4, it's considerably high already. And for arithmetic masking, you have other considerations. So how would you like to store the individual shares? You could store it either as signed integer or unsigned integer. So for example, if you want to store 7 mod 9, you could store this simply as 7, which is the unsigned representation. Alternatively, you could shift the upper half of all the possible values to the negative side. You do this by subtract the modulus from the upper half of all the possible values. And this way you have a range that is centered around 0. And we call this the center representation. And in this case, you could store 7 mod 9 as minus 2. And there has been a recent study that shows that if you choose to use sign representation, then the attacker might be able to learn more information about the secret that you are protecting. And because all the side channel attacks that we just mentioned on unprotected MLDSA, there has been masked MLDSA proposals. The state of the art are from two teams. One of them is closed sourced, is a team from XP. The other one is open source, which is nice. But they follow the same flow essentially. What they do first can be seen on figure one. They will first sample coefficients in polynomial y in Boolean masking. This is convenient because the coefficients of y follows a uniform distribution. And after you sample the coefficients in Boolean masking, you will convert it to arithmetic masking. And then from then on, never go back to Boolean masking. And then you will use masked y for various computations, sometimes in signed representation, sometimes in unsigned representation, depends on whichever is more convenient. Finally, output the signature z. And with this flow, then it naturally comes to our mind that can we still target this random sample y as unprotected implementation like before? And if we can still target it, how can we do this? I mean, now they are protected by various masking types. Sometimes it's stored in sign or unsigned representation. What would be the best choice for an attacker? And this is the main question that we would like to answer with our work. So first, let's drop any details of the attacker aside. Let's just take a look at what might be the maximum information that the attacker can learn by conducting an information theoretic analysis. And we do this with the following setup. So we focus on first order masking, so only 2 shares for individual coefficients of y. And then we chose the Hamming weight leakage model. This has been shown to be close to reality. And we chose 2 settings. The first one is noise-free. This allows us to analyze what is the maximum amount of information that the attacker could possibly learn. And then we have the more realistic scenario where we have a Gaussian noise. And in order to analyze and to quantify the amount of information that the attacker could learn, we use mutual information. And in particular, we compute the mutual information between 2 random variables. The first one is the secret that we are trying to learn, and we define, which is c times s1, and we define it as x. And the second one depends on the leakage function. For example, if we would like to analyze Hamming weight leakage, then this will be the Hamming weight of individual shares. If we like to analyze bit leakage, this will be the individual bits of individual shares. And with this definition now, let's think about how can we compute the mutual information. Before we go into the details, let's take a brief look on the parameters of MLDSA. So for MLDSA, you sample y uniformly random between roughly plus and minus gamma 1. Gamma 1 is a parameter. And then x follows a sum of uniform distribution, which is close to Gaussian. And it falls between plus and minus beta. And for MLDSA 44, gamma 1 is 2 to the power of 17. And beta is 78. So the following, and because z equals to y plus x, you have all the possible values that is shown below. But recall that we have to reject values of z that leak sensitive information. So out of this full line, only areas within the green block are acceptable. And areas outside in the red areas will be rejected. So for a accepted and published signature, values in the red blocks will never appear. So we only need to focus areas, or we only need to focus on values in the block in the green area. And it turns out that it's not that difficult. So once you are given a signature that has been published, then the value of z is fixed. And once z is fixed, because z equals to y plus x, and x follows this distribution shown on the right-hand side, it has only a small range of possible values. And once x has been decided, so is the value of y. So the distribution of y is the mirror distribution of x. And on the right-hand side, you could see the example. When the published signature z is 1000, then this will be the distribution of y. And what we covered so far is the case of unmasked, unprotected MLDSA. In the case of protected MLDSA, depends on the masking type. We will need to analyze individual shares. And if it's Boolean masking, then we can no longer just look at the value of y. So we need to iterate over all the possible values for an individual share. And for Boolean masking, this will be between 0 and 2 to the power of 18 minus 1. And once you decide the value of the first share, you fixed it. And because y has been picked earlier, then you could easily compute the other share. And this is the case for arithmetic masking as well. And once you have all the, and with this, you could iterate over all the possible combinations of z, x, y, and the first share n0 and the second share ny. And with this, you could compute the marginal distribution of the random variables you are interested in. In your case, there will be x, and the leakage function, and the leakage over individual shares. And with this, we could iterate over all the possible values of z and compute the average, which gives us the mutual information between the secret x and leakage condition on a published signature z. Of course, the leakage function depends on the representation. So for example, if you have a Hemingway leakage, then if you use unsigned representation for individual share, it might have lower value, because when you use signed representation, when it's a negative value, then you have a lot of positive ones in the binary representation. So we need to distinguish those two cases. And with the, now we know how to compute some mutual information, then we can take a look at the results. So this is the case when there is no noise. And in figure 2 and figure 3, we show the amount of mutual information between the leakage and the secret value. And this is the second order, where you have the attacker learns leakages from both shares. And as you could see, it doesn't matter what is the current value of z, the mutual information for Boolean masking is always higher than arithmetic masking. And it's also interesting to know that there is not much difference between signed representation and unsigned representation when we use arithmetic masking. This is not in contradiction with the paper that we just mentioned earlier. And this is just a more subtle case, because in this case, z is published. And in most of the cases, z has the same higher bits as y. So as an attacker, you actually get those bits for free. So the extra information that you learned when y is protected by signed representation, it's somehow, maybe not the best word, but somehow limited, because you know z already. But based on our computation, the signed representation still leaks a little bit more than unsigned representation. And you could see this on right here. So the upper table here is for the second order attack. And we also analyze accidental leakage. So what this means is that because the shares might be recombined because of compilation error, because of programming error, and the result of XORing both shares might become a source of leakage. And therefore, in the case of Boolean masking, the result of XORing those two shares together is directly secret value. But in the case of arithmetic masking, then you have a value that is related to the secret, but not exactly the same. So it's interesting to know that actually in this case, the attacker will also learn a bit of information about the secret that's been protected from accidental leakage in the case of arithmetic masking. But as in the case of second order leakage, Boolean masking still leaks more information, which is shown here, in the case of accidental leakage. And that was the case when it's noise-free. And when there is noise, this slide shows the results. So we changed the noise level, which is the standard deviation of the Gaussian noise. And the result shows that there is still not much difference between signed and unsigned representation. But regardless of the noise level, Boolean masking will still leak more will still leak more information for the attacker. And in particular, when the noise level is low, you could see that Boolean masking provides far more information for the attacker in comparison to arithmetic masking. And with this, we could draw this observation that Boolean masking should be the target for an attacker. And with that in mind, we would like to use belief propagation to try to attack protected masked MLDSA. So what is belief propagation? Belief propagation is, you can think of it as gossiping neighbors. The idea is that you are sitting at home, you have a teenager, and you don't know exactly what's going on. But luckily, you have gossiping neighbors, and then they will come around and then they will tell you, based on what I have heard, based on what I know, I think this is what is happening in your house. And if they do this daily, then you get a better and better information idea about what's going on in your house. And in terms of programming, what you have is this is a secret value S, and it has an initial distribution, and you have 3 noisy neighbors, x1, x2, x3. That depends on the secret. And the attacker learns side channel information about those noisy neighbors, and from there, they derive a bias distribution of the secret. They provide this distribution to the center node as a message, and the center node updates its own distribution accordingly. And if you do this over time, you will be able to harvest the tiny bias about the secret distribution. Hopefully, it will converge into one or only several values, and with that, you derive the secret value. We use the generic framework for solving learning with error problems proposed by Hamelin et al. And we instantiated with belief propagation. And it was originally instantiated for MLCAN as an example, and that works well. And we instantiated for MLCAN here, and it's open source. And it turns out that a direct instantiation for MLDS will not work because some of the distributions here, they are close to uniform. So here in figure 6, you have a distribution, the orange one derived from side channel. And you could see that the red dot is the secret, and it effectively reduces the possible range that an attacker will need to consider significantly. And on the other hand, in figure 7, you have a side channel distribution that is more close to uniform. It does not reduce the possible range for the attacker as much. And as you could easily see that this distribution is more useful for the attacker than this one. And in the worst case, when you have a completely uniform distribution, then it provides absolutely no information for the attacker. And in the ideal world, a uniform distribution will not affect our computation. It would just not modify the distribution of the secret. But because we need to use floating point computation to update the distribution, and it has numerical instability, so the more floating point values we have to process, the more likely we will run into numerical instability and therefore not being able to solve the result. So this is the reason why we will not be able to solve, to find the secret key S1 for MLDSA directly with the framework. In order to do that, we need to drop equations, which are distributions which is close to uniform, and we could compute this based on its entropy. The higher the entropy, the more uniform it will be. And by doing this, we were able to derive the secret key S1. And you could see that the filtering level can be quite tolerated. As long as we drop enough, let's say, less useful distribution, then the belief propagation will be able to harvest the tiny bias on the secret. And we could continue to do so, continue dropping distributions up down to a certain point where we drop too much information, and then we stop getting the secret key. And now we know what to do. We know we need to apply filtering, and with this, we simulate the attacks. So we simulate our attacks for both sign and sign representation. We simulate it for the first order attack on the Hamming weights of coefficient of y, and Hamming weights of coefficient of y in addition to the Hamming weights of the secret that we are interested. This is the best case for an attacker because you attempt directly seek information on the secret. And we also simulate the first order leakage on the least significant bits of y. And for the second order attack, we simulate attacks based on the Hamming weights of individual shares, and for shares that are protected in Boolean masking and also arithmetic masking. And this is a result. And what's interesting in figure 9 is that you could see that even when in this gray line here, even when the noise level is considerably high, the attacker will still be able to launch a second order attack on the first order protected MLDSA. And the amount of signatures we will need is not astronomical. And from the simulation, we know that we should be able to recover the secret key S1 with a reasonable amount of signature. Therefore, we sent out experiments. We ported the implementation from the open source MLDSA, masked MLDSA proposal for two microarchitecture, Cortex-M3 and Cortex-M4. And then we, because now we know Boolean masking is more interesting, we attack we launched the first order on attack on the Hamming weights of y and this significant bits of y. And we also launched the second order physical attack on the Hamming weights of individual shares. And the result can be shown here. Basically, we were able to confirm our simulation. And what's interesting is that for the second order attack, we only need 700 signatures to recover the secret key fully, and this is in line with our simulation here. And based on this simulation, we could expect that we will be able to solve the secret key S1 even when noise level is much higher with only 10K signature. So this shows that this is a noise tolerant second order attack. And with that, we come to our second, the last slide. To sum up, we show that like in this case, there's not much difference between sign and sign representation. And we show that Boolean masking is it just leaks more information regardless of the order of the attack in this case. So the first and second order. And we show that it's more likely to have strong accidental leakage. And we also show and verify by physical experiments that a second order attack on masked MLDSA can be noise tolerant. And finally, we show that it's important to use filters. So you don't want to include distribution that are not useful for your computation. And you could find more details in our paper. This is a URL to our paper, and this is a QR code for that. And thank you for your attention. I'll be happy to take questions.
We have time for one brief question as we are setting up for the next presentation. I will have a question then. The implementations that you attack empirically are supposedly protected and masked. Can you speak to how come they are empirically vulnerable?
Yes. So the reason why we were able to attack is because even though the implementation was verified secure in the so-called T-probing model, this T-probing model does not consider accidental first order leakage. And we were able to find one in one of the gadgets that they use. And you could consider a implementation error, but this could also occur even when you do it very carefully because of compiler optimization. But that is just the vulnerability. So the vulnerability that we use to show this that the first order attacks will work. But like for our second order attack, we did not have to use such source of leakage.
Thank you.
Thank you.
Our next presentation, as well as the two after it, will be online. You're welcome to stick around, and we will start with a presentation by Calvin Abu Haidar about Crowhammer, a key recovery attack on Falcon.
Hello everyone, today I'll be presenting you a joint work with Mehdi Tibushi and Quentin Payet that we called Crowhammer, a key recovery attack on Falcon. Let's start with a bit of trivia. On Falcon, it's a post-quantum signature scheme that has been selected by the NIST for standardization. It's actually now known as FNDSA. It is an efficient but complex scheme since it involves floating point arithmetics and Gaussian samplers. In particular, the Gaussian sampler of Falcon has been the target of many side channel attacks since it is notoriously hard to implement. And today we'll follow the trend and target the Gaussian sampler to perform key recovery on the scheme. So Falcon is a lattice-based signature scheme. More precisely, it's working with structured lattices. That is lattices that have some extra algebraic structure that will allow us to have a more compact representation of the elements involved and make our scheme more efficient. The lattices in Falcon are n-true lattices, and what we care about is the structure of the secret key. So what's a secret key in Falcon? It's a basis of the module we're working over and a Falcon tree. The Falcon tree will go into a bit of more details after on, so let's start by focusing on the basis. So the secret basis that you can see on the bottom left is comprised of small vectors. It is a good basis in the sense that I'll make a bit more clear later on. And the matrix you can see on the right is also a basis of the lattice, but it's a bad basis since it is comprised of, well, large elements, and bad in the sense that I'll explain also later. So how do you sign on Falcon? We'll start by explaining how the nearest plane algorithm works, since it is a simpler version of Falcon in some sense, and it is the basis of the design of Falcon. So in the nearest plane algorithm, we start with a basis of our lattice, here in dimension 2. We then compute the Gram-Schmidt orthogonalization of this basis, which gives us a basis of an orthonormal basis of the ambient space, but not a basis of our lattice anymore. This GSO basis spans a rectangle here, and what we can do is center that rectangle in our lattice point, and if we perform this operation for all lattice points, then we get a partition of the space. That is, if you take a random point in the space, you can find exactly one rectangle in which this point ends up, and compute the associated lattice point, so the center of that rectangle, if you want. This is exactly how we're going to sign here. So we take a random point in the space. It's going to be typically a hash of the message you want to sign. And we're going to perform, we're going to look for the lattice point that is in the same rectangle of that random point. And if we compute that point and we take the difference, this is going to give us, well, a short vector if our approximation is good, or a bad or a long vector if our approximation is bad. So that's why the nearest plane algorithm is used to solve what is called the approximate closest vector problem. That is, find a lattice point that is close to the random point, or at least close up to some approximation factor. So a good basis is a basis for which the approximation factor is going to be small, and a bad basis is a basis for which the approximation factor is going to be large. This signature process has been broken by Nguyen Regev in 2006, and the reason why it is broken is that you can always center the signatures in the rectangle around 0, and those signatures are going to be uniformly distributed in this rectangle, which means that if you take enough of them, you can actually recover the geometry of the rectangle. That is, you can recover the edges. And what Nguyen and Regev showed is that, well, you can actually compute the GSO out of many signatures. Falcon avoids this problem by adding some randomness. So the problem in the way of signing that I explained before is that it is totally deterministic, and it highly depends on the basis that we chose. In Falcon, the signatures are going to follow a discrete Gaussian distribution of covariance matrix transpose B times sigma times B, where B is the secret basis, and sigma is a parameter that we choose to avoid the leakage. So if we take the GSO decomposition of our lattice, of our basis, secret basis, if we select sigma in such a way, then the final covariance matrix is going to be little sigma squared time identity, where little sigma is a parameter that we can choose. We have to choose it in order to be able to sample the Gaussians, the final Gaussians. And it is independent of the basis B, which means that we will avoid the leakage of the previous attack. I mentioned the Falcon tree in the secret key. And this Falcon tree is actually a clever representation of this parameter big sigma, of this matrix big sigma. Instead of representing it as a whole matrix, we are going to leverage the ring structures to have a more compact and tree-based representation of this matrix. We care mostly about the values at the leaves, and these values are going to be the eigenvalues of this matrix sigma, so the values that are here. The strategy to perform Gaussian sampling is going to be to start by sampling Gaussians over the integers, using as input, as standard deviation, the values at the bottom of the tree. So these eigenvalues here. Once these half Gaussians are sampled, so they are half Gaussians since we can always turn a half Gaussian into a full Gaussian by just sampling a bit and flipping the sign, probability 1/2. So once we have those full Gaussians over Z, we're going to merge them in a way, again using the structure, in order to go up in our tree. And we're going to use the node value as a parameter. And until we reach, once we reach the root, we'll get a Gaussian sample over the ring. The implementation of the Gaussian sampling over the integers is, of course, constant time, and it is performed via a linear scan over a table. So this is like pseudocode for the Gaussian sampler, the half Gaussian sampler. We start by sampling a uniform element over 72 bits, and we have a counter S that we initialize to 0. And we're going to go through the table called RCDT, which stands for Reverse Cumulative Distribution Table. And each time an element of the RCDT is larger than our uniform sample, we're going to increment our counter by 1, and we're going to return the final counter. So assuming that the RCDT table has been filled up with the right value, this will give us half Gaussian over the integers. So one observation we had is that, well, if you have smaller entries in the RCDT, then the final result will be smaller, and so we'll have a smaller Gaussian, or at least a smaller distribution with a smaller variance. And our idea was that if you attack the RCDT to lower its values, you might cause statistical leakage. So instead of having the final Gaussian that is going to hide your distribution, your basis, well, if you target these values of the RCDT, probably you can make it so that the standard deviation becomes small enough that there is statistical leakage. And the tool we thought of using was the Rowhammer attack, which we don't really care how it works here, but we'll use it as a black box. And what it allows us to do is that it allows us to trigger bit flips in the RCDT. So we're going to be able to trigger some targeted bit flips, not many, but some targeted bit flips in the memory in order to turn 1 into 0. Now the question is, how many bit flips do we need to make an attack? So if we start only with the Nguyen-Regev attack, then if we consider a scenario in which we, empty the table, so that is, we turn it to full zeros, then, the Nguyen-Regev attack works, since it's very similar to what's happening in the nearest plane algorithm signature process that I presented you. But of course, this scenario is not realistic, since Rowhammer allows us to have some targeted bit flips, but there's way too many bits in the RCDT to perform that much bit flips. So one scenario that we considered is a scenario that was used by an attack on FrodoChem at CCS 2022. In this scenario, they performed 8 targeted bit flips on the keygen of FrodoChem. And if we consider these 8, if you allow us 8 bit flips on the RCDT, then the Nguyen-Regev attack does not work anymore. Of course, with the more, let's say, optimistic scenario of 1 bit flip, then the attack doesn't work also. So the question that we had was, what are the effects of the bit flips? And more precisely, how does the signature distribution behave with those bit flips? So one way you can see it is that we're kind of introducing errors in the Falcon tree, in the leaves of the Falcon tree. So of course that's not what's going on, since we never touch the secret keys, we only touch the sampler. But since we touch the base sampler, so the sampler that is performed over the integers using those values as input, it's as if we change those values. And the consequence on the matrix sigma is actually that the eigenvalues are going to be replaced. Let's focus on the distribution of the eigenvalues with respect to the number of bit flips that we perform. Let's start with 8-bit flips. We consider the basis over the module, but we could have considered also the basis over the integers. And over the integers in Falcon 512, the basis will have 1024 vectors. So if we take the GSO basis, the normalized GSO basis, the 1024 vectors will be eigenvectors of our covariance matrix here. And so they will have corresponding eigenvalues. And this is exactly what this graph shows. So the eigenvalues with respect to the index in the normalized GSO basis. What we can see is that there is a sharp decrease on the first part of the eigenvalues and a distinct sharp decrease for the right part. So this is due to the structure of the lattice of the basis, and we don't really care about it now. But if we consider one bit flip, we see the reverse pattern, so increase instead of a decrease. And what is important is that these patterns are consistent over the same number of bit flips. Let's come back to the attack of Nguyen Regev. The observation that we had was that the results that we had by performing Nguyen and Regev over the full dimension, so that is over the 1024 dimension basis, is that we had bad results. So we could not recover any relevant vector using Nguyen and Regev. But one observation is that the relevant eigenvectors live in a small subspace. And what I mean by that is that I didn't really go into the details, but we don't really care about the full matrix U. We don't really care to recover all the vectors of U. We actually need to recover very few vectors. Like, for instance, if we recover the first vector of U, we're done. If we recover the last vector of U, we're done. If we recover the middle vector of U, we're also done. So there's actually like 8 vectors that we care about. And so those vectors live in a small subspace. So probably one of the reasons Nguyen Regev fails is that the dimension is quite large. So the space might be too large for the attack to succeed. So one idea would be to improve the performances and probability of success by restricting ourselves to a smaller subspace. And now the problem is, how do we find this subspace? So if you come back to the eigenvalues for 1-bit flips, we could, let's say, consider that we want to recover the last vector. And we know that the last vector for 1-bit flip has a fairly high eigenvalue. So let's say we consider all the eigenvalues that are, well, larger than 100, or we could say the 32 largest eigenvalues, or 64, or whatever. And what we can do is compute these eigenvalues, the corresponding eigenvectors for our approximation matrix. So we have the real covariance matrix, sigma, and the space V, that is the space spanned by the eigenvectors corresponding to the k largest eigenvalues of sigma. So these values we don't know, but we get an approximation of these values. So we get an approximation of the covariance matrix sigma hat, and a space V hat that corresponds to like the space spanned by the eigenvectors that correspond to the k largest eigenvalues of sigma hat. And if those spaces are equal, so if V is equal to V hat, that what you can do is project the signatures that we have on V hat and perform the attack of Nguyen and Regev. But the problem is that in practice, we don't get this equality since we know that, well, the eigenvalues are going to converge eventually, so they're going to be close. But the behavior of the eigenvector, so of the spaces V hat, we don't really know how it's going to behave. So the question is, how close, for some sense of close, does it have to be for this attack to work? So one thing we can use is the Davis-Kahan theorem, or a variant of the theorem. And this is the the bound given by the theorem, so we don't really care about the details here. So how it applies in our case is that if we take V, the space, the eigenspace for the real matrix, and V hat for our approximated matrix, what the theorem tells us is that the subspaces are close up to this factor. So we don't really care what it means in detail, but what we can see is that the numerator is basically how close the eigenvalues are, and that we know how they're going to behave. We know that there will be convergence, and we can bound this. And the denominator is the important part. It also depends on the gap between the kth largest eigenvalue here, and the next one, the one that we did not consider. But the problem is that this denominator can be arbitrarily small, since we have no control over how the eigenvalues behave. And it seems to be a bit overkill, since in our case we only need one of the relevant GSO vectors to be in our space. We don't need the full space to be close to the original space, right? So one of our results is that we have a slight generalization of the Davis-Cohen theorem, where we say that the eigenvector v1 corresponding to lambda 1 is this quantity close to the space v hat, where the denominator has changed. Instead of having a gap between two consecutive eigenvalues, we have a larger gap, which is the gap between the largest eigenvalue and the one following our space. This gives us a two-step attack. The first is to compute an approximation, then project the signatures on the relevant subspace from the approximation and perform the Nguyen-Regev attack. Now, the question is it efficient? So for 8-bit flips, we need around 20 million signatures for the approximation step, and 2 million to perform the final Nguyen-Regev step. For 1-bit flips, we need around 10 times more. Now for countermeasures, we observed that the bit flips significantly reduce the signature sizes, and that since the bit flips are permanent in the RAM, the same signature process will be affected in the same way by the bit flips. So we propose lower bound rejection, akin to what is already implemented in Falcon, that is upper bound rejection. Since we will be able to observe the shift in the signature size, we can implement a lower bound for which we will reject signatures. And to ensure that the RCDT is still intact, we can also perform an integrity check, like a checksum by hashing the RCDT, for instance, or anything that is a bit less costly. Now what next? We have considered to extend this attack to other RCDT-based schemes, such as Oak. And we also considered, different ways to finish the attack to replace the Nguyen-Regev step. Thanks for watching, and I'll be there for the questions.
Questions to the authors can be conveyed by email, as for all online authors, and we will proceed straight to the next presentation.
Hello everyone, my name is Yu Wang. I'm from USDC. Our title is Leakage Resilience.
The next talk is on leakage resilient circuits against. The next talk is still about leakage resilient circuits against NC1, revisited by Yu Wang.
Hello everyone, my name is Yu Wang. I'm from USDC. Our title is Leakage Resilient Circuits against NC1 Revisited. A main goal in cryptography is to secure computational functions against adversaries who can obtain information about the internal operations. In practice, the adversary can obtain the information by using the side-channel attacks. To achieve this, we usually compile functions represented as circuits into leakage-resistant circuits. The functionality of an LRC, which is short for leakage-resistant circuit, should be the same as the original function. And it should be secure even if partial information of the computation is leaked. There are two main types of leakage-resistant circuits. The first one is stateless LRC. Let X and Y be the original input and output in a stateless LRC. The computation algorithm on input the encodings of X can output encodings that can be decoded to Y. The encoder and the decoder are assumed to be leak-free here. But all the wire assignments in the computation phase are exposed to some limited leakage. Its security guarantees that no information on X is exposed in the presence of leakage. Stateless LRC has many applications, such as computations performed by payment terminals and also implementation of zero-knowledge proofs. Another type of LRC is stateful LRC, which protects stateful functions. Here we call that in the stateful function, there is an internal state which is denoted by S here, and in each invocation it takes as input an external input X and outputs an external output Y. Also, it updates the current state from S to, say, S prime. Similar to the stateless LRC, a stateful LRC does not change the functionality of a stateful function. And we do not have leak-free encoder or leak-free decoder here. Instead, we only have a leak-free setup, which only encodes the initial state. All the other wire assignments are exposed to some limited leakage in each invocation. Its security guarantees that no information on the states is exposed. Stateful LRC can be used to continuously protect the key of a primitive, such as an encryption scheme or a signature scheme, where the key is stored in the internal memory. There are three main types of leakage models: the wire probing leakage model, the only computation leakage model, and the conditionally bounded leakage model. The latter two types of leakage are also called the global leakage. They are richer than wire probing leakage, but they are incomparable to each other. In this work, we focus on the computationally bounded leakage model. In this model, most existing works consider the AC0 leakage, where the leakage functions are circuits with constant depth. On the other hand, Miles and Wheeler consider leakage functions in NC1 which have logarithmic depth. This class is richer and more complex than AC0 leakage. They proposed both stateless and stateful LRCs, but both constructions rely on large leak-free hardware. Specifically, in their stateless construction, the size of the leak-free encoder is linear in the size of the original circuit. And in the stateful construction, their number of leak-free hardware components grows with the circuit size. So it's natural to ask whether it's possible to reduce the requirement for leak-free hardware in LRCs against NC1 leakage. In this work, we propose both stateless and stateful LRCs. The total size of the leak-free hardware components in both constructions are independent of the original circuit size. Our assumption is a very mild complexity assumption, which is NC1 is not equal to parity L/poly. It's weaker than the assumption NC1 not equal to L used by Miles and Wheeler. The leakage class we consider is the same as the work by Miles and Wheeler. Specifically, both constructions are secure against leakage functions in NC1 with logarithmic output length. Here we explain why we consider such leakage class in more details. At first, this leakage class captures all attacks modeled by AC0 leakage, such as the selective failure attacks, and it compromises all existing AC0 LRCs. Also, it can reveal the indices of wires carrying secret values or identify secret users. and it captures side-channel attacks in the high-mean distance framework. Finally, we know that NC1 captures polynomial leakage attacks with constrained memory. This is the overview of our constructions. We first propose a stateless LRC and then convert it into a leakage tolerant circuit with auxiliary input, which is denoted by AILTC here. At last, we convert the AILTC into a stateful LRC. We now explain how to achieve the stateless LRC against NC1. Our basic tools are two distributions, zero-sum and one-sum. Zero-sum outputs rank deficient matrices, and one-sum outputs full-rank matrices. The Grika and others show that they are indistinguishable against NC1 adversaries under the complexity assumption we mentioned before. And we further show that they can even fool NC1 functions with logarithmic output lengths. We omit the details here. And now let F be the original circuit with the input X and output Y. We first encode X by using the fine-grained fully homomorphic encryption against NC1. Here X is encrypted bit by bit, and the ciphertext CI for each bit XI is in the form in this picture. The public key is a matrix M, which is summed from zero-sum, and Ri is a random matrix. The capital letter I is the identity matrix. The computation algorithm just executes the homomorphic evaluation. The decoder computes the secret key and decrypts the output ciphertexts. Note that computing the secret key is hard for NC1 but easy for polynomial time algorithms. The correctness of our construction directly follows from the correctness of the FHE. But the security does not from the security of the FHE. The reason is that the security of the FHE breaks down when the homomorphic evaluation exceeds NC1. To solve this problem, we introduce internal wires for each gate gadget to refresh the output ciphertext by adding ciphertexts of 0. This allows us to construct a simulator in NC1 that can fool the leakage by using the public key M and the wires of the original circuit. Now we can switch the distribution of M from zero-sum to one-sum without being noticed. This means that M becomes a full-rank matrix now, and in this case, the ciphertexts of the input are uniformly distributed. Now the completion phase is completely independent of X, so no information on X is revealed in the presence of leakage. This is how we prove the security of the stateless LRC. We now show how to convert our stateless LRC into the AILTC. In the AILTC, there is a leak-free setup that outputs an auxiliary input. The computation algorithm on input the auxiliary input and the external input X will compute a correct value of the output, which is denoted by Y here. Its security holds if there exists a distribution over NC1 simulators that can fool the leakage using only X and Y. We now see why we cannot just use our stateless LRC as an AILTC. The main reason is that the decoder is not assumed to be leak-free in the AILTC, and thus the secret key for decryption will be exposed. So we cannot just switch the distribution of the public key M from zero-sum to one-sum in the secret proof now. To overcome this problem, we propose a new decoding algorithm, which is based on a fast Gaussian elimination process. For this decoder, we exploit the spatial structure of the public key M to show that all the internal wires of the decoding algorithm can be simulated by an NC1 simulator given M, the plaintext, and the internal randomness of the ciphertexts. Then we can use both the simulator of the new decoder and the simulator of the stateless LRC we mentioned before to simulate all the wires in NC1. This means that we can switch the distribution of M from zero-sum to one-sum and then make the ciphertexts uniformly random now. And now we can see that the computation phase is independent of the input X, and the decryption phase can be simulated by using Y. We additionally show that the encoding phase can also be simulated by using just X and the inverse of the matrix M, which means that all the wires in the AIOTC can be simulated using only X and Y now. Here there is a problem that the simulator of the decoder works only when the internal randomness used for encryption is kept hidden, but the randomness might be revealed in the computation. So we need to use auxiliary input generated by the leak-free setup, which are actually ciphertexts of zeros, to refresh the output ciphertexts. The size of the setup will be independent of the original circuit size, and it's only related to the output length of the original circuit. With this AILTC, we can obtain a state for AORC. Here we first show that the CPA secure fine-grained encryption proposed by Degrika and others is actually state for AORC. Here we first show that the CPA secure fine-grained encryption proposed by Degrika and others is actually too adaptively leakage resilient. Namely, it's secure against adversaries who can adaptively choose two leakage functions in NC1 for the encodings. Let f be the original stateful function. We adopt the framework used by Foster and others, and also Isha and Song to construct function f star based on the two adaptively leakage resilient encoding. Roughly, f star takes as input an external input X and an encoding CT to the current state S, and outputs the external output Y and also the encoding of the updated state, which is denoted by S prime. We then compile f star into an AIOTC. Here, the encoding of the initial state is generated in the leak-free setup. One can see that the leakage tolerance ensures that the leakage in each invocation can be simulated by only using the input, output, and the encodings. And the two adaptive leakage resilience of the encoding scheme ensures that the leakage on each encoding reveals no information on the states. Here we know that we need internal randomness for encoding in each invocation, but our AIOTC only supports deterministic circuits. A natural way to solve this problem is to use the opaque gates to sample encodings of randomness. But this will make the total size of the opaque gate squared. To address this, we show that the underlying encoding scheme has a composability property so that we can obtain encodings of randomness with only public points. Finally, we know that we can also convert our AIOTC into a stateful AORC with smaller circuit size in a non-black box way. This is achieved by using the re-encryption technique. Please see our paper for the details. Here is the comparison between our stateful and stateless ARCs and the ones proposed by Miles and Wheeler. One can see that our hardware components are independent of the original circuit size, so they are much smaller when treating moderately large circuits. Also, our assumption is weaker, and the other parameters are very close to each other. We additionally show that our AIOTC can be converted into a fine-grained NISC with offline simulation defined by Bo and others. Compared with the existing fine-grained NISCs, our assumption remains the same, but our verification complexity is minimal. Finally, we know that the reason that our stateful LRC still needs leak-free components is because the auxiliary inputs are generated with secret coins. So one may wonder whether it's possible to achieve stateful LRC without weak gates by constructing AI LTC with public coin setup. We show that this is impossible by proving the impossibility of constructing fine-grained ONISC with verifiable CRS, which in turn implies the impossibility of constructing AIOTC with public coin setup. So these are all our results. Thank you.
As before, questions can be directed to the authors by email, and we will proceed to the last talk of the session. We will change back from defenses to attacks. And the next talk to be presented by Nathan Maillet is about key recovery from side channel power analysis attacks on non-SIMD HQC decryption.
Hello, I'm Nathan Maillet and I'm going to present to you a joint work. Hello, I'm Nathan Maillet and I'm going to present to you a joint work with Cyrus Nugier, Vincent Miglior and Jean-Christophe Deneville. And it is in fact two attacks on HQC, which is quite on time as HQC has just been chosen to be standardized by the NIST. And in this standardization process, some side channels had been tampered, like time-based side channels, but power-based side channels were not. And here we present two side channel power analysis attacks on HQC, which implies a full key recovery. So to begin with, we didn't work on the optimized version of HQC sent to the NIST. We removed the SIMD, so the single instruction multiple data, which is done by a vector unit in your processor. And it's not baseless, as if you have some machine like an IoT friendly machine, well, you don't have for sure a vector unit, so you don't have any choice and you just have to remove this SIMD. So the SIMD-less implementation represents a portable and IoT friendly version close to what will be used in production with some IoT machines, right? It also happened that we made some comparison for the specific function that we are targeting, and for this function the SIMD-less implementation is faster, which can be explained because it happens that the compiler compiles it in less instruction than the optimized version. Sorry. So the throughput being the same, it's quite normal to have a cycle count lower for the SIMD-less implementation. And to begin with, well, we can do a quick reminder of HQC, which is a PKE, so a public key encryption mechanism that's being used as a KEM, so as a key encapsulation mechanism in the NIST process. And what we are attacking is the PKE version of HQC, so this implies also an attack on the KM version of HQC. And here we have Alice and Bob sends a message to Alice. And as HQC is a code-based crypto system, when Alice receives the ciphertext, which is U and V, she computes V minus UY and does the decoding based on the code of HQC. And in fact, we can see it as two decoding, the first part being Reed-Muller decoding and the second part being Reed-Solomon decoding. And the function that we are targeting is at the beginning of the decoding when Alice receives the code word, so it's in the Reed-Muller decoding part. And it will be useful later, so any vector in HQC can be viewed as a polynomial. And here, the Y part in the V minus UY is part of the secret key from Alice, right? So as HQC has been in the standardization process of the NIST, some previous attacks and some history is already made on this part. So HQC changed during the standardization process and changed the code it's using. So here are some attacks with the newest code HQC is being using. Most of the attacks are on the reference implementation, which is quite important because the reference implementation is not meant to be used in production and is not meant to be secure against any side channel. So what's really interesting is to target an optimized version of HQC, and here it's only attacks at the architecture level. So one of our attacks is on the architecture level or the ASA level, and is shown here. So what we need is only one oracle call, which means that only with one execution of the decoding of HQC we can fully recover the key, and it's being done on the optimized version of HQC without the SIMD. It's the first power side channel analysis that we know since HQC changed its code. And as I said, there is two attacks in our contributions. So the first of them is at the architecture level, and in fact, depending on the optimization flags you are using and the architecture that you are targeting, well, the attack will not be exactly the same, and so we needed two variants of the same attack to be successful in our architecture level attack. So that's the first one, and the second one is on a real hardware. It's being made on a Cortex M4 microarchitecture, and we will see later that it's a different attack from the architecture level attack, where it's using the same idea behind it. And in this case, 83 traces are enough to ensure full key recovery with 99% of chances for any HQC version. So we also proposed some countermeasures. We looked at three of them, in fact: the minimal distance decoding, adding noise, and code masking. And it happened that well, they can be taken independently, and they are enough to work around and mitigate our attacks, but they can also be used to mitigate other attacks. And for the papers from CHESS 2022 and CHESS 2023, well, those papers only attack the KM version of HQC, so it's normal if it doesn't mitigate those, because our attack is only at the PK level of HQC. And if we start with the architecture level attack, well, we can dive a bit deeper in HQC's code. So HQC's encoding takes a message and apply some read Solomon code. Then it encodes it with a readmuller as it's concatenated and duplicated. The decoding part of HQC is just the other way around, right? So we just have the encoded message, and when Alice receives it, she computes v minus uy, and this v minus uy that's being computed and used between the duplicated part and the readmuller read Solomon encoding code word, well, it's being leaked, and I will show it to you later. And this value is a sensitive value. To show that it's a sensitive value, we can start with assuming that v minus uy is known, so it could be known by side channel, and let u be invertible. Then it is easy to see that we can fully recover y and x, which are both the part of the secret key of Alice. Then we made some security reduction. So for all u, it does not need to be invertible. Well, you can recover y and x, and to recover y, you only need to do a brute force, and the force of the brute force needs to be of n, which is the length of the code of HQC's code, minus the rank of the circulant matrix of u. Because in HQC, multiplication between vectors can be seen as a multiplication between a vector and a matrix, which is a circulant matrix. And this value, n minus the rank of the said matrix, is the number of bits needed to brute force in order to recover y. So this could be really useless if this value is really high, but it could be really interesting if this value is low. So what we are showing next is that the rank of the circulant matrix of u can only take 4 values: 0, 1, n minus 1, or n. And in fact, the 0 and 1 values nearly never happen. like we made 5 million samples to test it, and on those samples none of them were of a value of 0 or 1, and it was quite 50-50 for the values from n-1 and n. So what those theorems shows is that either you don't need to do a brute force to recover y, and so x, or you just need to do a brute force of length 1. So it's quite easy, right? And well, that being said, v minus uy is a sensitive value, but how can we recover this v minus uy? We still need an oracle to give it to us with side channel. So if we look at the C code of HPC at the beginning of the decoding, we have this function, exponent sum, which is done at the beginning of the Riedmüller decoding, and it's using the v minus uy by blocks of 16 bits, and in those blocks of 16 bits, it's computing on each bit one by one. This could be really interesting from a side channel point of view, but we still have to look more about it to ensure that there is a side channel at least at the architecture level. So if we look at the assembly code from the inside of those loops, we have 4 instructions, and we can do a step-by-step execution of this code in order to see what happens to the registers and if there is some leakage. If we look at the T1 register, what the values it takes is the values of the sensitive value v minus uy, which is named with its bits because it's a 16-bit block, and it is named from B15 to B0. And when you do some execution, at the execution step I equal 14, well, what you have is that the register T1 takes the value B14 and only 0, and then when doing the right shift at this instruction, just after the right shift, what you have is that you have a transition from a 0 to B15, and this transition induces a leakage transition which allows you to recover the B15 bit. Then, in order to recover all bits from the sensitive value for this block, what you have to do is that you roll back, and what you can see is that for each step, the transition in the T1 register only depends of what you leaked before and what you are working on now. So you are leaking bits bit by bit by doing the execution backward. Then we made some microarchitectural attack, like we have done the attack on real hardware, and what happens here is that it's even easier than the architectural level attack, because when you do so, you only have 2 Gaussians of the power consumption, and those Gaussians are only dependent of the bit computed. It's not dependent of the previously bit, so you don't have you don't need the knowledge of other bits. You only have to know if your computation corresponds to a 0 or to a 1 for each bit, and you can do so for the whole 16-bit block and for each block of v minus uy. So with this method, it's quite devastating because it's really easy, and you have some statistical results from the power traces. Then if you do so on the whole block and on the whole blocks from the sensitive value v minus uy, what you have is that you need multiple traces in this case, because the real hardware has some statistical noise, and what we can see is that with more or less 80 traces, you can be sure that you have the fully recovered the v minus uy value, and then you can just redo what we have done before with the architectural level attack to recover from this y and x, which are the secret keys. So then what we have done is that we looked at some countermeasures. The first of them is the minimal distance decoder, so the distance being the Hamming distance, And the idea behind this is that we can compare all code words to find the nearest one to the input, and this will fully replace the Riedmüller decoding. So in principle, it's quite easy. What we are saying here is that the exponent sum function is leaking, so we just have to remove this function, right? If we remove this function, an attacker can't use our attack. Quite easy. And next, another idea we had is the adding noise idea, which is when Alice receives the ciphertext, Alice samples and adds some random noise, some random error, and the idea is that if an attacker picks on the exponent sum as we are doing now, he won't get the v minus uy value, he will get the v minus uy plus some error. And with this countermeasure, we still need to control the weight of this error. It has to be such that n choice the weight of e prime prime is way greater than 2 at the power of your security level. And what's really interesting with this countermeasure is that if you only take 11 for the weight of this error, well, the DFR, the decryption failure rate, nearly doesn't change. So it's really interesting. Next, what we looked at is the code word masking. So the idea is pretty much the same. What you do is that you let the attacker pick on the result, but the result won't be v minus uy, it will be v minus uy plus something it doesn't know. And so when Alice receives the ciphertext, she computes m prime and m prime times g to add it to the v minus uy. And to ensure that those countermeasures can be used, well, we have done some TFLA tests with 30 samples, and none of them leaked something. Thought if we go a deeper, if we dive a deeper with the TFLA test with 100 samples, well, it seems that the minimal distance decoder could be leaking something, so we still have to analyze it, but the adding noise and code word masking does not. And this was done with a simulation, so there were no noise on the TVLA test, which is quite interesting. We also made some rough comparison of our countermeasures to have some idea of the overhead it would cost if you implement it. So it's just to have an idea, right? So we have done so on the reference implementation of HQC. And well, this sum up a bit our countermeasure. And thank you for your attention. I'll be online if you have any question.
Technical sessions. The next non-technical session will take place on a Kappa lawn and involves strawberry chocolate.